Hello everyone, we're back with another installment of C++ real-time audio programming with Bela. Where we left things last time is that we were looking at processing audio in blocks of samples rather than one sample at a time. One of the reasons we were interested in processing audio in blocks is that we wanted to create effects using the fast Fourier transform, or FFT. The FFT lets us create a class of audio effects collectively known as the phase vocoder, and that's what we're going to pick up with today. We'll see that the phase vocoder is an incredibly powerful way of transforming our audio signals, letting us do things like pitch shifting, which we couldn't easily do with filters alone. This lecture is the first of a two-part series on the phase vocoder, building on the block-based processing architecture we saw in Lecture 17. In today's lecture, we'll review how to segment a real-time signal into blocks or windows, and we're also going to look at how to work with windows that overlap with one another. The difference between last lecture and this one is that we're going to look at both the input and the output side of the equation. In other words, not only how to break the signal up into windows, but how to put those windows back together again into a new signal. This process of reconstructing a signal from an overlapping series of windows is known as overlap add, and it's the basis of quite a number of block-based audio processes. In this lecture, we'll also have a first introduction to multi-threaded audio processing. We'll see why this is a useful approach to dealing with expensive computations that occur relatively infrequently. By the end of today's lecture, you will create an architecture for building phase vocoder audio effects, which implements the overlap add process. We'll see just a couple very simple applications of the phase vocoder today, and in the next lecture, we'll look in more detail at what we can do with it. As usual, you can find the companion materials, including the code examples, at the GitHub link at the bottom of the screen. To run today's code examples, you'll need a Bela starter kit or a Bela mini starter kit. Today's lecture doesn't require any external hardware or other components. Now, in the last lecture, we looked at what we meant by block-based processing. We were looking at calculations that needed to be run periodically on a group of samples. So here, in this case, we might wait until 512 samples have arrived, and then do some sort of calculation on all 512 samples at once. We would not then repeat the calculation until we had the next 512 samples, and so forth. We drew a contrast between this process and filtering, where we had to calculate a new output each successive audio frame. To see an example of how this block-based process works, let's take a case where our real-time audio buffer size is 8 samples and we want to process something in blocks of 6 samples. What we're going to do is we're going to fill up this input buffer or array with samples one at a time as they come in. So for example, in our Bela render function, inside the for loop that we usually write, we might copy samples from the audio input into this buffer. Once the buffer is full, then we can pass it along to our block-based process. We then empty the buffer and start all over again with the next 6 samples, and so forth, where every 6 samples we call the block-based processing code. Remember from the last lecture that when we talk about block-based audio processing, our block or window size is not the same thing as our real-time audio buffer size, and that's why we were always copying the audio samples from our audio input into a buffer that we controlled, and only once that buffer was full did we call our block-based process. As we discussed, the most common reason to use block-based processing is that we want to take a fast Fourier transform, or FFT, on our audio signal. The FFT is an algorithm which efficiently calculates the mathematical structure called the discrete Fourier transform, and this was a way for us to measure the frequency content of a window of signal. Recall from the last lecture that any finite length signal can be represented as the sum of sinusoids. In this example, we have 16 points in time. And we saw that this particular signal could be represented as this sinusoid of 0 frequency, plus this one of frequency pi over 8, plus this one of frequency 3 pi over 8, plus this one of frequency 5 pi over 8, plus this one of frequency 7 pi over 8. We add all of those together with the right amplitudes and phases, and we exactly reconstruct the original 16 points. We saw that the discrete Fourier transform was a way of extracting the amplitudes and phases of each of the frequency components that makes up this signal. Because we have 16 input samples, the DFT might produce up to 16 sinusoids, but in this case only these 5 components are meaningful. We can see why if we look at the output of the DFT itself. Here we have 16 output samples which correspond to the amplitudes and the phases of the components. The first sample of the DFT corresponds to the first frequency component, the second sample to the second component, and these 3 samples correspond to these 3 frequency components. The other components we see in the DFT here either have a value of 0 or they're the mirror image of the components that we already have. Again, what we're doing with these Fourier transforms is that we are taking a finite length window of signal over time, and we're decomposing it into sinusoidal components, giving us the amplitudes and the phases of each of them. The frequencies of these components are actually standardized by the DFT itself. We know that they are linearly spaced between a frequency of 0 and 2 pi, therefore given by the expression 2 pi k over n, where k is greater than or equal to 0 and strictly less than n. We called each of these outputs of the DFT a bin, and collectively the bins are known as the frequency domain representation of the signal, in contrast to the typical samples over time, which is known as the time domain representation of the signal. An important principle from the last lecture is that the DFT does not actually give us a different signal, rather it's better to think about it as a different mathematical perspective on the same signal. What it does is transfer n samples in the time domain into n samples in the frequency domain. There is also an inverse discrete Fourier transform which does the opposite, n samples in the frequency domain back to n samples in the time domain. And as long as our DFT has at least as many points as the original time domain signal we're working with, we can always get an exact reconstruction of that signal by taking the DFT and the inverse DFT. If you haven't already watched Lecture 17, I would encourage you to do so to get more context on this process. We're also going to come back to the meaning of each DFT frequency bin in the next lecture. What's new for today is the idea that we not only want to divide up a signal into discrete windows, we also want to take those windows and reconstruct a new signal out of them. The typical way that this works is that we'll isolate a window of signal. We'll do some sort of processing on that block, for example an FFT and inverse FFT, and then when we're done with that processing, we're going to take the resulting block and stitch it together with the other blocks into a new output signal. In the most basic case, if we haven't done any processing on each block, it should be possible to stitch the blocks back together to reconstruct the original signal exactly. Now, the most typical application for this process of windowing and reconstruction is the phase vocoder. In brief, what this means is that each time we generate a block of signal, we're going to take an FFT on that block. We're going to do some sort of processing then in the frequency domain, which involves the phase of each of the frequency bins. Then once we're done with that frequency domain processing, we'll take an inverse FFT to get a new time domain window. We can then mix those windows together into a new signal at the output. And this is what we're going to look at in this lecture. To extend our example from the previous lecture, what we're trying to create is a system more or less like this. We have an input signal, which we'll call x of n. It's coming in real-time blocks of 8 samples. Now remember, our real-time system block size is not necessarily the same thing as our window size for block-based processing. And here, we're going to try to process x of n 6 samples at a time. So we're creating 2 buffers, or arrays. One I'm calling the input buffer, the other I'm calling the output buffer. And we'll stitch the 6 sample windows back together into a new output signal y of n. So here's how that works. We'll have a write pointer which keeps track of where we store samples in the input buffer. And as our real-time samples come in, we're going to copy them from x of n into the input buffer. Once the buffer is full, then we have a block of signals. We could apply a window function to this block, which we'll talk about later on, and then we could run some sort of block-based process like an FFT on it. The block-based process will produce another 6 sample window of signals stored in the output buffer. It's then our job to copy those samples from the output buffer into our new signal y of n. To do that, we'll need to keep track of a read pointer, which tells us which sample to read in our output buffer. So far, then, we've seen one complete window, assembled, processed, and put back into the output. Once that's done, we empty our buffers and start all over again, copying 6 samples into the input buffer. Once that's finished, we can apply a window function, run some kind of block-based process, generating an output buffer, and then once again we copy the output buffer into y of n, and we can go along like this 6 samples at a time indefinitely. Now, this is a very nice idealized view of how a block-based process should work, but we have a problem. The problem is that this system isn't causal. Let's see what I mean by that. A causal system is one where the current output only depends on the current input and previous inputs. A causal system cannot have an output ever depend on a future input. Now, we were running calculations on 6 sample blocks at a time and storing those back at the same point in time as we found them. So x of 0 through x of 5 ultimately produced y of 0 through y of 5, and so forth with the other blocks. And here we see the reason that this isn't causal. The output sample y of 0 depends on the input sample x of 5. That means it depends on a future input, which isn't allowed. Now you might reasonably look at this diagram and say, well, what does it really matter? Because x of 0 through x of 5 are all inside the same real-time audio block anyway, so we really do have access to all 6 of those samples at the same time. So I would suggest to you that there's another example on this very slide where an output y of n for a particular real-time block depends on an input x of n, which only comes in the next real-time block. Where might that be? An example here would be y of 6. You can see that calculating this requires all 6 input samples x of 6 through x of 11, but x of 11 won't be received until the next real-time block. So essentially the problem is that we cannot run this system in real time because we often need to know what happens in future real-time blocks before we can calculate the output. So one partial solution to this is to deliberately add a latency to the system, and we can add a latency that is exactly as long as one window, like this. The idea here is that we don't need any of the outputs of the block-based process until at least one sample after all the inputs have come in. So while we're gathering input samples for one window, we're busy copying samples from the previous window into the output, and this way the system will always remain causal. Now, I'll come back a little bit later on to why I call this only a partial solution. We'll see why adding this amount of latency is not ideal in terms of being able to run our block-based calculations in real time. But before I get to that, I want to look at a common case, which is where our windows overlap. In the previous example, there were no input samples shared between blocks. We also saw that the larger the block size, the less frequent the calculation would have been performed. But for a whole variety of reasons, it's often useful for the blocks to overlap each other. One reason that we do this is that we want to use longer FFTs, but calculate them more often. We'll see why we do that in the next lecture. We'll use the term hop size to describe the interval between the calculations, in contrast to the window size or block size. It's very common in FFT-based processes to have the hop size be an integer division of the window size. It's also very common before we calculate the FFT to apply a window function to the signal. What this means is that we take our window of signal and we multiply it by some function which typically has tapered edges. In the next lecture, we'll talk about what windows we commonly use and why we do this. Ultimately, what we're building up today is a very standard approach for block-based processing, which is known as overlap add. You'll see shortly why we call it that. Here's the way this works. Suppose we have an input signal. We're going to isolate from that signal a single block using a windowing function. Here, the black dashed lines indicate the hops, and the window size is equal to twice the hop size. Once we have that block, we will take an FFT on it. The FFT needs to be at least as long as the number of time samples in the block. If it's longer than the number of time samples, we just add zeros to the end of the block before we take the FFT. The FFT will take us from the time domain into the frequency domain, and the idea is that then we do something interesting in the frequency domain. We're not going to talk about this today, but it'll be the focus of the next lecture. Once we've finished our frequency domain processing, we take the inverse FFT, which will give us a new time domain segment. Now what happens at this point is that we don't write the segment directly to our audio output. Instead, we are going to add that segment into an output buffer which also contains the results of the previous segments. And then, once we've done that, we're going to advance by one hop, and we're going to repeat the same process all over again. And we repeat this each hop, where our processing consists of an FFT, some sort of frequency domain effect, and then an inverse FFT, and each of the outputs we get are added together to produce the output signal y of n. So remember that this process is called overlap add. The add part of it comes from the fact that each of the windows, when we're finished processing, gets added together into the output buffer. The overlap part comes from the fact that the hop size is less than the window size, therefore the windows are going to overlap. Building up a reliable overlap add infrastructure is the main task of this lecture. First, let's look at what we need to do on the input side, getting windows out of our signal. This is a review of the last time. Our goal was to work with blocks that overlapped one another, such that subsamples in block K would also be shared with the previous block K-1. And what we came up with was to keep a running history of our inputs, such that at any time we could always retrieve the last m samples. We have a data structure which does exactly this, and it is, of course, the circular buffer. So by storing our input signal in a circular buffer, then every time a new hop elapses, we could pass the most recent m samples from the circular buffer to our FFT, and this is how we did it. The circular buffer, you'll recall, is just an array of memory with a right pointer that tells us where the most recent sample can be found. Every time a new sample comes in, we overwrite the oldest sample and advance the right pointer, wrapping it around as necessary. Alongside storing our samples in the circular buffer, we were also keeping a counter of how many samples had elapsed since the last hop. Once the count reaches the hop size, then we extract the most recent window, which can always be found just prior to the right pointer. The problem that we had is that this most recent window was not necessarily stored in consecutive order because the circular buffer could always wrap around. That meant that we needed to copy the samples from the circular buffer into a new buffer, which was always ordered sequentially. The other thing we needed to remember about implementing this in code is that there was no significance to the point at which the circular buffer wraps around. Our hop size probably has nothing to do with the size of the circular buffer itself. When it came time to unwrap the circular buffer, here's what we needed to do. It was actually stored in memory as a linear array with a right pointer telling us what the most recent sample was, and what we needed to do was to copy those samples into a new buffer in increasing order. That meant that our copying routine had to be aware of the wraparound of the circular buffer. We saw this in the previous lecture using modulo arithmetic to work out where to take the samples from the circular buffer. We saw all of that in the previous lecture. What's new this time is that we are also attempting to generate an output signal based on the results of our block-based process. To make this work, we need to declare an output buffer which is different than the system audio output, which is going to hold the results of our overlap add calculations. Every time we get a new window of signal coming out of the block-based process, we add it into this output buffer. Samples can then be copied from the output buffer into the system audio output once all of the windows that they depend on have been calculated. So here, the first 6 samples of x of n are passed to a block-based process. The output of that process is added into the output buffer at the beginning. If our hop size is 4 samples, then the next block will overlap the previous one by 2 samples. We can calculate a block-based process on those 6 samples and add it into the output buffer. And we can go along like this, each hop adding the results into the output buffer. Now remember, our output buffer is just an intermediate storage location. It's not the system audio output, so we don't yet have a causality problem. Perhaps the most important thing to emphasize about the output buffer is that certain samples can only be calculated as the sum of different windows. This is because our windows overlap. To implement the output buffer, we can use another circular buffer like we did with the input. However, we do need 2 separate buffers, one for the input and one for the output. Now, to work with the output circular buffer, we're actually going to need to keep track of not 1, but 2 different pointers. The right pointer is going to be telling us where each new block gets written in the output as it's calculated. The read pointer, by contrast, will be telling us which sample we are copying from the output buffer into the system audio output. The idea here is that the right pointer is going to move by jumps. Every time a new hop takes place, we'll copy a new block of samples into the output buffer and the right pointer will jump ahead. Meanwhile, the read pointer will be incrementing 1 sample at a time as we're unspooling the samples from the output buffer into our system audio output. To do this right, we need to make sure that the read pointer never gets ahead of the right pointer. That is to say, we're never trying to read data that we haven't finished computing yet. So, as we get samples in, we'll see if process unfolds something like this. Each successive audio frame will read 1 sample at a time out of our output buffer. And just as the read pointer is about to reach the right pointer, a new hop will take place. The hop will cause a new block of samples to be calculated and added into the buffer, and the right pointer will advance by 1 hop. We can then continue to read from the output buffer and send it to our system audio output. Notice that some of the samples we're reading are the sum of 2 different blocks. Once we finish reading a block of samples, we should clear them in the output buffer to ensure that once the right pointer next wraps around, it starts from a clean slate. We'll continue reading frame by frame until we reach the next hop. That will again produce a new block of samples which is added into the output buffer, and we'll continue reading 1 sample at a time, clearing the outputs as we read them. To implement this output circular buffer, here's what we need. The size needs to be at least 1 window size plus 1 hop size in length, although there's no performance penalty to having it be longer, and that can give us a bit of extra margin. If we had a multi-channel audio effect, we'd need to replicate the structure once per channel. Implementing the output circular buffer involves an array of memory plus 2 pointers, as we saw, a write pointer, which tells us where the next block is supposed to be stored, and a read pointer, which tells us where we're pulling samples out of the buffer and putting them into our system audio output. The way we handle the processing, then, is once we finish calculating an inverse FFT, we need to add that window of samples into the output buffer, starting at the location indicated by the write pointer. Remember, we're adding it to what's already there in the buffer. We are not replacing the contents of the buffer. This is core to the overlap add idea. Simultaneously, as we are iterating through our real-time audio samples, we should be copying samples from the output buffer into the system audio output. That might be in the for loop inside of render. Each time we've copied a sample out of the output buffer, that's a good time to set that sample in the buffer to 0. That means eventually, when the write pointer in the circular buffer comes back around to the same slot, we've started from a clean slate. We increment the write pointer once per hop by the hop size, and we increment the read pointer once per real-time audio frame by a value of 1. Putting it all together then, this is our block-based processing signal chain. We have an input x of n, an output y of n, both of them coming in real-time audio blocks. We are processing them in blocks whose size might be different than the real-time audio buffer size. Partly for that reason, and also because the blocks overlap, we need to have a buffer at the input and a buffer at the output. The input buffer has a write pointer, which tells us where we're storing samples as they come in. The output buffer has 2 pointers. It has a write pointer telling us where we're storing the blocks, and a read pointer telling us where we're extracting the data from. Now the processes highlighted here happen once every audio frame. One sample of the output buffer is stored into y of n, and the read pointer advances by 1. By contrast, the process in the middle, which is our block-based process, only happens once per hop. This is where we extract a window of samples from the input buffer, apply a window function to it, and then run some kind of block-based processing, such as an FFT effect. Once we get a new block of samples out, that is then added into the output buffer at the location given by the write pointer, which then advances 1 hop. The result of all of this process is a series of overlapping windows at the input, producing a series of overlapping windows at the output. And as shown here, the system is causal, because each output sample only depends on current and previous input samples. That takes us to our first task. The goal here is going to be to implement the diagram we just saw as code. Most of this structure is already given to you from the previous lecture. Our job is to implement the output circular buffer. The variables have been declared for you at the top of the file. You'll find a vector of type float, which is the array, a write pointer, which keeps track of where the block should be written, and a read pointer, which keeps track of where to copy samples into the audio output. You'll see that compared to last lecture, the process FFT function has been updated to take not 2 arguments, but 4. It takes the input buffer, the write pointer for the input buffer, the output buffer, and the write pointer for the output buffer. Copying the result of the inverse FFT into the output buffer is already done for you. The code that you need to add is inside of render. You need to be copying samples from the output buffer into the Bela audio out. That will involve the read pointer. After you've copied a sample from the output buffer into the Bela audio output, it's important that you set that slot of the buffer equal to 0. Then finally, you'll need to increment both the read and the write pointers of the circular buffer. Remember that they don't both behave the same way. One moves every frame, the other moves every hop. When you first finish this and it's working, the sound should be exactly the same as it was before, with no modification whatsoever. At that point, you can also try engaging an effect called robotization. The code is already implemented inside of process FFT, it just needs to be uncommented. We'll talk about how that effect works in the next lecture, but it gives you one early simple example of what we can do with a phase vocoder. Pause the video here. Alright, here we have the completed FFT overlap add example. Let's just start by looking at some of the global variables that have been declared for us. We have the FFT processing object, which we saw in the previous lecture, and we have declared our FFT size, which is 1024 samples, and our hop size, which is 256. We also have our input buffer, which we discussed in the previous lecture, and its size, which is considerably larger than needed. Because the input buffer is a circular buffer, we need to keep track of a pointer where we're writing at the moment, and then we have our hop counter, which is separately going to be used to determine when we need to calculate the next hop. We have added, in this example, an output buffer. This is also a circular buffer, and as we saw, it needs two pointers. It needs a write pointer to tell us where we're going to write each new block when they come in, and it needs a read pointer to tell us where we're pulling samples out of the buffer and putting them into the system audio output. Let's next go down to the render function and see the code that we needed to add. Here we have our usual for loop in the render function, counting through the number of frames in this real-time audio buffer. The input code is what we've seen before in the previous lecture, and I won't cover that again. This now is the code that we needed to add. Here, we're using the read pointer to read the current sample from the output circular buffer, and we're storing that into this variable called out. That will subsequently be written into the system audio output. Then it's very important that once we have read the sample out of the circular buffer, we reset that sample back to 0. That's because every time we get a new block, we're not replacing the contents of the buffer with that block, we're adding it into what's already there. So we need to clean up after ourselves as we go along. This line of code just scales down the amplitude of the output to account for the fact that there are several blocks overlapping in the output. Then the other part we needed to implement was handling the increments of the pointers. As we saw, the read pointer should increment one frame at a time, and when it gets to the end of the circular buffer, it needs to wrap around back to 0 again. Remember that wrapping around the end of the circular buffer is not a significant event in terms of when to run our calculations. What is a significant event for running our calculations is when the hop counter exceeds the hop size. Of course, we have to start by resetting that counter back to 0, and then we have to call our process FFT function. Here, notice that it takes 4 arguments rather than 2. The last time we saw this, we only had to pass in the input buffer and the input buffer's pointer. Here, we also have to pass in the output buffer and the output buffer write pointer. We're choosing the write pointer here because that's what's telling us where the next block should be added into the buffer. Finally, once the process FFT function is done, we have to update the write pointer. The write pointer updates by skips of the hop size, so you can see that we're adding the hop size to the write pointer here, and we take a modulo operator by the buffer size to ensure that we don't fall off the end of the circular buffer. Then, at the end, we write our input sample to the left channel, our output sample to the right channel, and then we log both of them to the scope so that we can see the difference in time once it's running. Let's run this code now and see how it works. You should be able to hear that we have the same signal on both channels, but that the left channel is just slightly ahead of the right channel. This is the latency of our block-based process in action. Let's go over to the oscilloscope and we can see how much it is. To see this more clearly, we'll change the controls so that we can see the edges of the signal. We'll zoom out a little bit. And then let's also set the trigger so that it gives us a more stable plot on the screen. There we go. Now we can pause this plot and close the controls, and we should be able to see here the difference between the left channel in red and the right channel in blue. And we can calculate from here what the latency should be. So notice at the top there's a label that says x is equal to minus 3.9 milliseconds, and then here we have x is equal to 19.05 milliseconds. So we add these together and we find that there's about 23 milliseconds of latency between the input and the output. Now we might ask, how many samples of latency is that at 44,100 samples per second? And you can multiply it out, 44,100 times 0.023, and you get that it is 1,024 samples, exactly the FFT size. That's precisely what we expected, and that's really good news. Now I want to look back at our code to see why that latency works out that way. We'll stop this. And if we start by going up to the top of the file again, you can see that our write pointer and our read pointer for the output buffer differ by one hop size. That is 256 samples. Now that might seem a little bit confusing. We were expecting a latency of 1,024 samples, but apparently these pointers are only 256 samples apart. So what is going on? Well, there's two effects that contribute to make it so that our latency is actually one FFT size. The first of these comes from the render function. Let's go down there first. Now let's think about where our pointers will be when the first hop elapses. The first hop is not going to take place right at the beginning of the program. Rather, it's going to happen when 256 samples have gone by, causing the hop counter to equal the hop size. At that point, our input buffer pointer will have moved 256 samples, and our output buffer read pointer will have also moved 256 samples. In other words, by the time the hop elapses, that difference between the read and write pointers of the circular buffer will have disappeared. So that will not contribute to any of the latency. So where does the 1024 samples of latency come from then? It actually comes from the process FFT function. Let's go there now. Notice how we're calculating the circular buffer index in our input buffer. When we're unwrapping the circular buffer into our input of the FFT, we're starting from one window size prior to the input buffer pointer. That is to say, we're looking backwards 1024 samples. On the other hand, when we're copying the output of the FFT into the output buffer, we're starting straight at the output buffer pointer and moving forward. In other words, there's a one window size latency between input and output inside the process FFT function itself. And as we discussed, that is the theoretical minimum that we can have in running a block-based process. So everything works out as we would expect. You might also find it interesting to try running the robotization code just to hear what that sounds like. I'll say in advance that this is not the most sophisticated or refined version of this effect that we can achieve. We're going to improve it in the next lecture by using some window functions, but let's hear what it sounds like anyway. So you'll hear this time in the right channel that the drums have acquired a constant pitch. When you apply this to a vocal signal, you should hear that the voice is very intelligible, but its pitch information has been lost. The pitch depends on the hop size, and we'll look at this more in the next lecture. Next, I want to call your attention to a subtle but very important problem when working with block-based processes. To discover this problem for yourself, go to the settings of the Bela IDE and change the real-time audio block size to something quite small like 4 samples and rerun the program to see what happens to the audio output. Pause it here. So I'm back here to my code, and I'm going to go to the settings pane, and I'm going to change the block size from 16 audio frames down to only 4. And now when we run it, we're going to see what happens. Notice all of the underruns here and the slightly broken up sound. This indicates that we're constantly missing our real-time deadlines. This is a real problem. Let's have a look at why this happens when the block size becomes small. Here again was our signal chain involving the input and the output x of n and y of n, 2 circular buffers for the input and output, and a block-based process in the middle that runs once per hop. Now the problem sneaks in right here. How long do we have to run our FFT, IFFT, and any frequency domain processing? The answer is just one sample. We cannot start the processing until x of 5 has come in, but we need to have the result available by the time that we want to generate y of 6. So we might ask why this would be a problem, or conversely, why did this ever work in the first place with a larger block size? The problem we're going to run into has to do with intermittency of CPU load. In the early lectures, when we looked at the computational requirements of running audio code in real time, we were assuming that the CPU load from one sample to the next was roughly constant over time. But in the case of block-based processing, that's very likely to be false. We might have a situation where even though the average CPU load is something that we could calculate in real time, the instantaneous load at particular times means that we can't meet our real-time deadlines. Let's take an example where we want to calculate an FFT once every 10 samples, and suppose that this is how long it takes to run the FFT. If our real-time buffer size is 8 samples or larger, we're fine because the amount of time it takes to calculate the FFT is less than the interval between real-time blocks. And remember that whenever we call render with a new block of audio, we already have access to all 8 samples of the block. However, if our real-time buffer size was only 4 samples, we have a big problem. The FFT takes longer to calculate than one call to render is allowed to run. So whenever the FFT takes place, we're going to end up with an underrun because we don't meet our real-time deadlines. So the problem is that we have a heavy CPU load that only comes up occasionally, while most calls to render actually do next to nothing at all. What do we do about this? To start with, one precondition is that we have to add enough latency in our output that we don't need to generate the results within one sample. However, that's not going to solve the problem by itself because we still have this issue where the FFT takes longer than a call to render is allowed to run. The solution, aside from increasing the real-time buffer size, is to move the expensive occasional process out of render into another thread. The idea is that the render function will always run with the highest priority, but the FFT calculation will take place in a different thread of execution which is only allowed to run when render is not running. Let's see why this is a solution. Here's our signal chain again, but I have added an extra 4 samples of latency between input and output. That's equal to 1 hop size. So now, instead of only having a single sample to finish our FFT calculations, we have one entire hop to do this calculation. That gives us a more comfortable margin. As for how to implement the threads, we're going to build on an API that Bela provides, which is in turn based on the ZenMI real-time Linux kernel that we run. ZenMI provides a real-time threading system which works in a fairly straightforward way. Whenever there are multiple threads active, the thread with the highest priority number is always going to run first until that thread is finished. At that point, the next highest priority thread can run, and so forth. All of these ZenMI threads will have a higher priority than standard Linux code, which is running in what's called secondary mode. Secondary mode threads will only run when there are no ZenMI real-time threads available to run. The Linux scheduler is responsible for determining which of these secondary mode threads runs at any time. This is a fairly complex topic and not one that we're going to talk about in this lecture. Instead, I want to keep focused on the most important thing that we need to know for our block-based processing, which is that we're going to have 2 ZenMI threads. The higher priority of the 2 threads is already given to us. It's what calls our render function each block. Our job inside of render is the same as it ever was, which is to do our processing as quickly as possible and then return so that the system can work on other things. The lower priority of the 2 threads is going to be where the process FFT function is called. Process FFT will not be running all the time. It will only be called occasionally when there's a new hop. It's expected that this is going to take a longer time to finish than any call to render. Therefore, it only runs when render is not actively running, taking up whatever extra CPU time is available. Here's how that looks in practice. We have a block size of 4 samples, and each time we have a new block, we call our render function. The blue bars are an indication of how long the render function takes to run. As you can see, it's a small fraction of the total block size. Then separately, we have another thread running the process FFT function. We were calculating FFTs every 10 samples, so once we get to the third of the real-time blocks, then we can start the process FFT function. It will not finish before the next call to render, but that's okay, because when render runs again, that thread will take priority and the process FFT calculation will simply pause until there's CPU available to run it again. That pausing and resuming is completely transparent to our code. We don't need to worry about saving the state of where we got to. The code will simply stop executing when render needs to run, and then it'll come back and pick up where it left off as soon as render is finished. Now, of course, process FFT only runs occasionally, and when it's done, it's done. The most efficient way to handle the thread running process FFT is to have the thread exist all the time, but most of the time the thread is simply sleeping. That is to say, it's not using up any CPU. While the thread sleeps, it waits for a signal. The signal is a notification that we send from a different thread, in this case from the render function, telling the FFT thread to wake up and do its calculations. Now, because we're not calling process FFT directly within render, we have to worry about how to get the data from render into the other thread running process FFT. What we'll need to do in render is store the relevant data into global variables that we can pick up from process FFT. Those global variables should not be disturbed by future iterations of the for loop inside of render. In other words, the FFT thread needs to be able to discover a snapshot of whatever data we had at the time the FFT was supposed to begin. Once the FFT-based code has finished running, its output should be stored into the output circular buffer, and then process FFT can simply return, the thread will go back to sleep and wait for another signal to render at the next hop. To expand on the previous point about capturing snapshots, the challenge that we have is that the render function can interrupt process FFT at any time during its execution, and we don't have any control over when that might take place. That means that any variables we need to calculate the FFT should not be disturbed by future iterations of the for loop within render, or indeed by future calls to render. In practice, with our overlap add code, the main place this comes up is with the write pointer into the input circular buffer. The write pointer tells us where the newest sample in the buffer is stored. But by the time we get a chance to call process FFT, we might not want to be working with the newest sample. Rather, we only want to be working with samples up to the end of the previous hop. As long as the input circular buffer is big enough, we don't care that there's a few newer samples also stored that we're not going to use. But we need to cache the value of the write pointer at the time that the hop elapsed. That means that process FFT can find the right window of samples to work with. Fortunately for the simplicity of our code, the interruptions can only run in one direction. Render has the higher priority, so it can interrupt process FFT, but not the other way around. That means we never need to worry about the render function itself being interrupted by other code. Now let's look at how we make a Bela program use two threads. As we discussed, Bela provides an API for creating and manipulating ZMI real-time threads, which are also known as tasks. Each Bela real-time task is going to require 4 different pieces of code. First, we're going to need to create a global variable of type auxiliary task. This is the data structure that holds information about the thread. Second, we need to write a function which this thread will run. The function needs to have a special format. It needs to take a single argument of type void pointer, and it does not return a value, so has type void. The third thing you need to do is to call the Bela create auxiliary task function inside of your setup function. Again, this is something you do once at the beginning of your program. This will initialize the auxiliary task object with all the information that it needs and get the thread ready to run. You need to specify a couple arguments here. One is which function should be run by the thread, and the other is the real-time priority. Valid priority levels are between 0 and 99. Render runs with a priority of 95, and in almost every circumstance, you'll probably want the priority of your auxiliary tasks to be lower than the priority of render. The last thing you need to run a second thread is to make a call to the function Bela schedule auxiliary task. You do this whenever you want your function to run. Oftentimes in Bela code, you'll schedule your auxiliary tasks from within render, but it doesn't have to be that way. Remember that if you are calling schedule auxiliary task from within render, that function is not going to run right away. It will only run once render is finished and its higher priority task has gone to sleep. It's not so simple to directly pass arguments into the function that you're calling in a separate thread. Rather, the simplest way of communicating is to have global variables that are shared between the two tasks. Now, if you're not careful, this can also get you into quite a lot of trouble if one thread is modifying a variable while the other one is trying to use it. We'll look more at that situation and what we can do about it in a later lecture. And that brings us to our final task of this lecture. In the companion materials, you'll find a project called FFT Overlap Add Threads. This project extends the previous one by moving the FFT calculation into a second lower priority thread. A lot of the threading infrastructure is already done for you in this project, but your task is twofold. First, inside of the render function, you need to schedule the auxiliary task which runs process FFT. This should take place once per hop. Second, you'll find a function called process FFT background. This is what the auxiliary task actually runs. You need to finish implementing this function so it passes the right arguments to process FFT and it handles the pointers in the correct way at the end. When you're done, as before, you'll hear the input signal in the left channel and the output signal in the right channel. If the code is working correctly, you shouldn't hear any difference between the two channels except for a slight delay. Pause the video and try it. Here now is the threaded version of our overlap add code. There were two things we needed to do. First of all, we needed to schedule the FFT thread each hop, and second of all, we needed to fill in the function called process FFT background. Before I get to either of those, let's just have a look at how we initialize the threading itself. That's given to us here with this variable of type auxiliary task. This is Bela's specific API for working with real-time threads. We also have this variable called gCachedInputBuffer pointer. We're going to use this in the render function to remember where the circular buffer was when the hop counter elapsed, so that the render function can continue running and process FFT can pick up from the right place once its thread has a chance to run. We've declared a prototype of the function that the auxiliary task is going to run, and that function is declared down here in process FFT background. We'll come back to its contents in a second. The last thing we needed to do to initialize the auxiliary task was here inside of setup, where we're calling the function Bela create auxiliary task, passing it which function to run, its priority, and a unique name that the system can use to identify it. Alright, now let's go look at how the task is scheduled. Inside of render, once the hop counter elapses, that's the place that we need to schedule the background task. So you can see that our hop counter works exactly as before. We reset it to 0 when we reach the hop size. And then what we're going to do is, instead of calling process FFT here, we're going to schedule the auxiliary task which is going to run when it has a chance, which is to say when render finishes. But as we've discussed, the problem that we'll have is that input buffer pointer is going to continue moving each iteration of the for loop up here. We don't want that to happen because we want to make sure that the process FFT function finds it at the right place for the hop. Therefore, we're storing the current value of input buffer pointer into this variable gcached input buffer pointer, and that's what we're going to pass to process FFT. We can then go to the process FFT background function, which is what the auxiliary task is calling. Its job essentially is to call process FFT with the right arguments and then update the right pointer as we would have previously done inside of render. So the arguments here are very similar to what they were before, the notable difference being that we're passing gcached input buffer pointer rather thanginput buffer pointer. Finally, we are updating the output buffer's right pointer exactly as we were before. The contents of process FFT haven't changed in this case, it's just running in a different thread. One thing that has changed is our latency. As you'll recall, we needed to add 1 additional hop's worth of latency to make sure that we had time to run our calculations. That is being handled up here, where we're starting the output buffer right pointer 2 hops in advance of the read pointer. We discussed in the last example why this is not the actual latency, twice the hop size, but in fact the latency will be equal to 1 FFT size plus 1 hop size, which we can verify in just a moment. So let's run this code and have a listen. So with our drums running, we can now go back over to the oscilloscope and see what's going on. We have to unpause the display that we had from before. And now I'll pause it again and close the controls, and we can again read off the latency from the difference between the red and the blue plots. So this is at about minus 4.1 milliseconds, and this one is at about 25.1 milliseconds. So we're in the neighborhood of 29 milliseconds or so. And if you go do the calculations, you should find that 29 milliseconds is basically exactly what you would expect for 1024 plus 256 samples at a sample rate of 44,100 hertz. So everything's working out as expected. That brings us to the end of the first of this 2-part series on the phase vocoder. Today we mostly focused on the time domain, setting up the overlap add infrastructure that we needed to implement the phase vocoder. In the next lecture, we're going to look at what actually happens in the frequency domain and how we can use this to create interesting audio effects. We'll look at window functions, including how to implement them and which type of windows we might want to use. We'll also look at the meaning of the frequency domain data, especially the phase of the FFT bins, and we'll see how we can apply this to a series of phase vocoder effects, including the robotization effect that we briefly saw in this lecture, and others. The main thing we'll build up in the next lecture is a pitch shifter, which changes the pitch of a sound without changing its timing. This is something that can only be done with block-based processing. In the meantime, don't forget to subscribe to our YouTube channel to be notified of the new videos, and you can find us, as usual, on social media or at any of our websites. We'll see you soon for the next one.